Welcome, deep divers. Today we're really plunging into something absolutely central to our energy future. The world's pushing hard for renewables, and one technology keeps coming up: the heat pump. Vital, yes. But how well do we really understand their role in the big picture? Our mission today is to unpack a really specific and I think important piece of research. It's called Impact of Temperature Dependent Coefficient of Performance of Heat Pumps on Heating Systems in National and Regional Energy Systems Modeling.
Huh.
It's a bit of a mouthful, sure, but it gets right to the heart of how we model these heat pumps and what that actually means for getting to 100% renewable energy.
And that modeling, it's not just, an academic thing. It's really fundamental for integrating different energy sectors. We're talking power and
Yeah.
heat primarily. Getting that linkage right is key for a flexible, fully renewable system. And this study, well, it helps us get a much clearer, more accurate picture. It shows why the details really matter for planning.
Okay, let's unpack this a bit. What's the sort of typical way energy system models have looked at heat pumps or HPs? Often it's been pretty simplified, right? Like using a generic heat pump model and just one number for its efficiency, the coefficient of performance, or COP.
Exactly. And this study points out that simplification really limits our understanding. It means we might not be properly capturing how, say, hourly temperature changes affect efficiency, or even how different types of heat pumps perform, one in your home versus one used in industry. They're not the same.
Yeah.
And the risk there is underestimating the HP capacity we actually need and maybe getting the energy demand figures wrong too.
Right. So just quickly for anyone listening, COP, that coefficient of performance is basically the ratio of heat you get out versus the electricity you put in. Efficiency, essentially. Higher COP, more efficient. Simple as that.
But the fascinating thing, and what this study really zooms in on, is how much that comp depends on the temperature difference. The difference between where the heat pump gets its heat, the source, like air, water, ground, and where it delivers it, the sink, like your radiators. Ideally, you might see a COP of like 8 or 10. But real-world pumps, maybe 3 to 5, under similar conditions. And there are losses, defrost cycles, all sorts. The study uses these simplified formulas, but they're derived from actual regression analysis of data to calculate COP for different types: air, water, ground, based on that real temperature cap,
Yeah.
not just theory.
And that's a novelty here, isn't it? This study is specifically looking at how that hourly temperature-dependent COP plus differentiating the HP types, how that changes the results when you model the whole energy system. It's moving beyond the averages. So to test this, the study uses Finland as a case study. Why Finland? Well, it's a perfect, if challenging, place, wouldn't you say? Cold, long winters, really high demand for space heating. Continental climate, but with Atlantic influences too. It's a tough environment for heat pumps.
It really is. And they set up 4 scenarios to compare things. There was a base COP, just a single number from the literature, then mean COP, slightly better, using an average of the hourly values, then the key one, hourly COP, calculated based on the actual ambient temperature each hour. And finally, industrial HP, which added specific industrial heat pumps on top of that hourly model. It lets you see the effect of each step.
And Finland's climate really highlights the issue. I mean, this study found that in the absolute coldest periods, down to maybe minus 35 Celsius, wow, air source heat pumps can see their COP drop as low as 2.
Exactly. And that's precisely when you need the most heat. Peak demand, lowest efficiency. That's a real challenge for the system.
Okay, so here's where it gets really interesting. How do these more detailed COP calculations actually change the big picture, the energy system itself?
Well, the findings are pretty significant. This study found that using those simplified COP values, the ones from literature, it can lead to a substantial underestimation of primary energy demand, PED. That's the raw energy input. We're talking as much as 5.8% underestimation in the heat sector alone by 2050, and about 1.6% for the whole integrated system. Now, the overall cost of the system, or its total efficiency, might not change massively, less than 1% impact on costs, the study found. But underestimating primary energy demand by nearly 6% in heating, that's a big deal for planning and ensuring you have enough resources.
And the study also points to these subtle but really significant shifts in the technology mix, right, with the hourly COP model. The system seems to rely more on wind power and utility-scale batteries, and less on solar PV and thermal storage. That seems a bit counterintuitive at first.
It does, but it makes sense when you think about it. With hourly COP, the electricity demand for heating becomes much more variable, spiking when it's coldest, often when there's less sun. Wind power tends to be stronger in winter, so it aligns a bit better with that higher winter heating demand. And the utility-scale batteries, they're crucial for handling those rapid short-term fluctuations in demand caused by the varying HP efficiency. They can react faster than, say, large thermal stores. So the system optimizes leaning on wind and fast-reacting batteries to balance that more volatile heating load.
Okay, that makes sense. And what about for individual homes versus district heating systems? Does the detailed modeling change things there too?
It does. For individual heating, the model actually suggests slightly less total heat pump capacity installed across the board. Instead, you see an increased role for biomass heating, especially in a place like Finland, with lots of biomass resources. It acts as a backup or alternative during those really cold, low-COP periods. For district heating, large HPs seem to struggle a bit more to compete economically in this detailed model. Things like cheap electricity for electric boilers, biomass, or using waste heat often look more attractive, especially when HP efficiency drops.
So thinking about operations, what does this mean for how the grid actually runs hour by hour?
Right, the operational changes are key. With hourly COP, the system doesn't just run HPs constantly. It optimizes. It actively avoids using them when their COP is really low because it's inefficient and likely expensive. Instead, it might ramp up biomass heating or maybe charge thermal storage either at home or centrally during periods of high COP or when electricity is cheap. So the heat output from HPs becomes much more variable, much more dynamic. It's responding to conditions.
And that dynamic operation must have knock-on effects, right? It's not just the heat pumps themselves.
Absolutely, a ripple effect.
Yeah.
You see much more activity, more throughput in thermal energy storage systems as they buffer that variability. And it creates more variable electricity demand from consumers, these prosumers,
hmm
which in turn places greater demands on the main grid storage, like those utility batteries we mentioned, and requires more sophisticated grid management overall. It adds complexity, but it's a necessary complexity for efficiency.
The study also really emphasized the need to treat industrial heat pumps differently, didn't it? Not just lumping them in with residential or district heating.
Yes, that was a crucial finding. Unlike maybe district heating HPs, which face competition, industrial HPs look really competitive in this analysis. The studies suggest they could supply something like 9% of industrial medium and low temperature heat by 2050. That's significant. Their big advantage is often utilizing waste heat. Think e-fuels production, for instance, which might have waste heat around 70 degrees C, perfect source temperature for an industrial HP to upgrade. By using that waste heat, they directly substitute other energy sources and actually reduce the overall electricity demand from industry.
And that reduction has wider impacts. The study showed adding industrial HPs reduced the need for solar PV capacity by about 9%, while wind stayed pretty stable. It really shows how specific applications, like using waste heat in industry, influence the whole electricity generation mix. Everything's connected.
Exactly. And if you tie it all together, this study makes a strong case that using these specific HP types, modeling their actual temperature-dependent performance, it gives a much better estimate of their real potential and impact. That industrial HP scenario, for example, led to a 1.8% lower primary energy demand across the whole system compared to the simpler models. Detail matters. It leads to better planning.
So let's wrap this up for you, our listeners. The core takeaway here seems clear. While getting into the weeds with heat pump modeling hourly COP, different types might not drastically slash the overall system cost. It fundamentally changes how we understand energy demand, the best mix of technologies, and crucially, how the grid needs to operate, flex, and balance itself hour by hour to make a renewable future work.
Absolutely. This study really provides strong evidence that this kind of detailed modeling should be the standard, the target, for energy system analysis going forward. It's not just adding complexity for complexity's sake. It delivers genuinely valuable insights into the pathways for transition and the statistical roles these different heat pump technologies will play.
Which leaves us with a final thought, doesn't it? If a country like Finland, with lots of biomass, sees these kinds of significant shifts just from modeling heat pumps more accurately, what does this imply for other places? Regions with different climates, maybe fewer local resources, different grid structures. How much might we still be getting slightly wrong in our global plans if we stick to the simpler models? Definitely something to think about. You've been on the deep dive exploring the impact of temperature-dependent coefficient for performance of heat pumps on heating systems in national and regional energy systems modeling. Hope you found that useful. See you next time.